Okay, so the motivation for this video. I'll be introducing two functions, the metric and the inner product. And so these are two functions which take in two vectors as inputs and output a real number. And so the way that they'll be used later on is our inner product will be our secret tool in understanding Fourier series. And our metric will come up a little bit later on when we consider the convergence of Fourier series functions. Yeah, onward to the video. Okay, so in this video we'll be discussing a little bit about the generalization of what are called metrics and inner products to more general vector spaces, which we talked about in the last video. So what is a metric? If you've heard of the word metric before, it's probably in relation to the metric system. And so the metric system is a system of units and conventions used to measure things. So metrics in math always give you a way to measure the distance between two objects. So whenever you hear metric, you should think of like the distance between two things. So formally, a metric is a function d, which takes in two vectors as inputs, that's what this v cross v means, and then gives you a real number as output. So we'll go over a couple examples of this, but first let's state the axioms. So first you have that the distance between any two vectors, which is when you take u and v as your inputs, that must be a real number which is greater than or equal to 0, so it's a non-negative real number. And if you have that the distance between two vectors is 0, then the two vectors are the same vector, or conversely, if you have that the two vectors are the same, then this means that the distance between them is 0. So these make sense because you don't want a negative distance between two objects, and you want the distance between an object and itself to be 0, obviously, because you don't want that to be positive. So together, these two conditions are called positive definiteness. This condition just states that if you have the distance between u and v, that's the same thing as the distance between v and u. So this is just saying that it shouldn't matter whether you measure the distance starting from u and going to v, or starting from v and going to u. They should be the same both ways. And then this one is the most interesting condition, and it's called the triangle inequality. And it says that the distance between u and w, for u and w being vectors, is less than or equal to the distance between u and v plus the distance between v and w, where v is any vector. Could be u, w, or some other vector that's separate. So one example of a metric, or like this idea of distance, is say you have a couple of cities and the distance between two cities is the shortest path between them to drive, for example. So here we have three cities, A, B, and C. So let's say that the shortest road between A and C is this road, the shortest road between A and B is this road, and the shortest road between B and C is this road. So what this triangle inequality tells us is that the distance between A and C is at most the distance from A to B and from B to C, because by definition the distance is the shortest path between them. So if B were on this path, so if B were like right here, then the distance from A to B plus the distance from B to C would be the distance from A to C. But otherwise, since B is out here separate from this path, you can find a shorter path from A to C other than traversing from B in between. So that's sort of the logic behind this triangle inequality. And the reason it's called the triangle inequality is because of our first example, which is the Euclidean metric on your Euclidean vector space, which is denoted r to the n. So your Euclidean metric is your usual Pythagorean theorem metric, which is that you have some points which you can consider as vectors, and the distance between 2 points is the sum of the differences of the components squared, and then you take the square root of all that. So for example, if you have 3 dimensions where u is some vector u1, u2, u3, and v is some vector v1, v2, v3, then the distance between u and v is u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. And so in this case, the triangle inequality literally tells you that if you have a triangle, then the sum of two of its side lengths is greater than or equal to the third side length. The second example here is Hamming distance on Bitstrings. So this is sort of separate from what the main point of these videos are, but it's a nice example, and I'm pretty sure it's one of the first examples where the idea of a metric was used. So what are bitstrings? Bitstrings are just strings of digits of ones and zeros. So they're just a bunch of ones and zeros put together. And here you consider bit strings of a fixed length. For example, all bit strings of length 3, which are 3 ones or zeros next to each other. So the distance between two of these things is the number of differing digits. So for example, if you have the two strings 101 and 011, then the distance between them is 2, because the distance between them is the difference of digits, and you have the first digit is different, the second digit is also different, but the third digit is the same. So that's why you get the 2. And so you might not think that this is much of a different distance conceptually, but one thing that you can do is put all of your bit strings on a unit cube like this. So that if you move this way, you change the third digit to a 1. If you move back, you move the second digit to a 1. And if you move up, then you move the first digit to a 1. And so here, if you look at 101 and 011, 101 is up here, 011 is down here. And so this 2 means that you need to go at least 2 edges to get from 101 to 011. So it's the least amount of edges that you need to move across to get from your first number to your second number. So another thing that you might be complaining about is that this isn't a vector space. But if you remember, I sort of glossed by this, but a vector space can be over any what's called a field. And if you know some number theory, then the field that this is a vector space over is the integers modulo 2. And so addition is just component-wise addition. So you can think of like these bit strings as being vectors. So it's like this is a 3-dimensional vector, but the elements are integers mod 2. And so here you have 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 1 is 0. And so this is interesting because for computer science, this corresponds to the XOR operation. So here, if you have like false plus true, that's true. Or if you have true plus true, that's false. And also multiplication is kind of useless here, but essentially if it's just component-wise. So it's like scaling, but in these integers mod 2. So 1 times anything is itself, and 0 times anything is 0, 0, 0. So the Hamming distance, I'm pretty sure, was used for some sort of, like if you have some data that you're transferring from one location to another, the Hamming distance was sort of used to figure out if any of that data was like destroyed or like messed up in the transfer. So for these first two cases, it's pretty obvious that the distance is greater than or equal to 0, and that the distance between two things is 0 if and only if the two things are equal. The second part, you can check for the Euclidean metric if you don't believe that. And then this symmetric thing is also pretty obvious, but the triangle inequality, I leave for you to try and figure out. And this one's a bit more fun, and this one's a bit more algebraic. So the third one is a metric on our vector space of continuous functions, which we discussed on our last video. So continuous functions on the interval AB form a vector space because remember that you can add them and you can scale them up by some value. And if you have any sort of objects that satisfy those two things, then you can consider those to be a vector space. So here the distance that we have between two functions is the maximum of this quantity over your interval AB. So what that means is, like, say you have your function f of x is this line and your function g of x is this parabola. So here at every point x, you look at the difference between these two functions, and here is where the distance is maximized between the two functions, and so that is your distance between g and f. So to sketch a proof of the triangle inequality, you can say that, okay, take any point x, and then here denote the distance between f of x is up here, g of x is the middle one, and h of x is the bottom one. So denote the distance between f of x and g of x as delta fg, and the distance between g of x and h of x at this point as delta gh. So here I called it delta instead of d because we're just picking a particular x value, but the d, which is your distance function, is your maximum of all these deltas as x varies between a and b. But anyways, for any particular x value, you have, just looking at it, this length plus this length is this length. So you have that delta fg plus delta gh is less than or equal to delta fh. And so if you like rearrange the order of the functions, you can convince yourself that this less than or equal to actually holds. And so since your d is just your maximum of all these deltas, this implies this inequality, which is, of course, the triangle inequality. And this one is a bit maybe more interesting to see this d uv equals 0 if and only if u is equal to v. So this is saying that the distance between two functions is 0 if and only if the two functions are the same. So that's another interesting thing to think about. So yeah, that's all I want to talk about metrics. Let's now talk about inner products. Okay, so now let's discuss what an inner product is. So an inner product is the generalization of the idea of a dot product in Euclidean space. So when we talked about metrics, we said that a metric was sort of a way to measure the distance between two things, right? And in Euclidean space, it's our usual notion of distance. We also saw a notion of distance for Bitstrings and a notion of distance for functions. So an inner product sort of generalizes our dot product idea of projections that we saw in the first video. So the inner product provides sort of a computational tool for figuring out how much of one vector projects onto another vector. So an inner product is a function which is denoted by these two angle brackets, and then the two vectors go into here, which is what this v cross v is again, and then the output is a real number. So that's all this notation is. It's a function which takes in two vectors and gives you back a real number. Here I put a little asterisk with the complex numbers because later on we'll be looking at vector spaces with complex coefficients, which means that the scalars or the numbers that you can scale up by aren't real, they're complex instead. So I'll point out the differences here, but they won't be too important for now, and if you don't understand them right now, that's fine. So the first axiom is that if you take the inner product of u plus v comma w, then that's the inner product of u with w plus the inner product of v with w. The second axiom is that if you scale up u by some scalar a, so a is a real number, then this is a times the inner product of u with w, which is the inner product of u with w scaled up by the same number a. This property is the inner product of x and y is the inner product of y and x, which is pretty easy to check for Euclidean vectors. And then this one is also called your positive definite condition, which says that the inner product of x with itself is greater than or equal to 0. And if the inner product of x with itself is equal to 0, then that implies that x is equal to 0. So here 0 represents the real number, and here 0 represents the 0 vector. So remember that every Euclidean vector space, or sorry, not Euclidean, every vector space has a 0 vector, which sort of acts like an identity. So if you add the 0 vector to anything, you get it back itself. So that's what this 0 is, and it says that the inner product of 0 with itself is 0. So we'll see later why this is important. But these two conditions together form what is called the linearity condition. And if you combine this condition with this condition, this also tells you that if you add up two numbers in the second argument, so if you have like u comma v plus w, then that's the same thing as u comma v plus u comma w. So here, these asterisks, if you work over the complex numbers, this works a little bit differently, that you have to complex conjugate this value a. And here, you have to complex conjugate the value of the inner product. But again, we'll get to that later on, so it's not too important for now. So these seem kind of weird as axioms to go with, so I'll sort of explain it in terms of our Euclidean vectors, since there isn't really another good example of an inner product other than the one that we'll be using for Fourier series. But that'll come in the next video. So if we have two vectors u and v, and we have a third vector w, then remember the inner product of u and w and the inner product of v and w sort of give you the lengths of these projections. So it's not exactly that, because you also have to divide by the length of w squared, but I just left out that part for just intuition purposes. So here u comma w sort of gives you this length, and v comma w gives you this length. So you can add those two together and get this total length. But what you can also do is first add up the vectors, and then take the inner product of u plus v and w to get the length itself again. So the difference is you can either take the projections themselves first and then add up the projections, or you can add up the vectors first and then take the projection of the added vector onto the new thing. This property is just that if you project u onto w, and then you scale up u by some factor a, and then you project this new vector au onto w, then this new length is going to be a times this length. So like for example, if you triple the length of u, then the projection will also be tripled in length. This property is kind of more interesting. It's that the inner product of u with v is the same thing as the inner product of v with u. This isn't a very good graphical, there's not a very good graphical intuition that I know of. I'm pretty sure 3 Blue 1 Brown did a great video on why that holds. So I'll probably link that down below. And then this property will explain why that's important now by talking about a metric induced by an inner product. Okay, so the last topic I want to introduce in this video is the metric induced by an inner product. So what does this mean? That means that if we have a function, which is our inner product, which sort of acts like a projection, like a function that tells you how much one vector projects onto another vector, from that we can get a different function, which is a metric. So it'll give us a sense of distance. So why is this important? Well, the inner product is going to be our tool in understanding Fourier series. So it'll allow us to break down a function into different components. And from that, we can get a distance between functions. So a way to describe how far away functions are from each other, which is separate from the maximum norm or the maximum distance that we had earlier. And so the reason that that's important is because we'll be dealing a lot with infinite series. And for the convergence of anything, if you haven't taken calculus, convergence is just like if you have a ton of things and they're getting closer and closer to something. To describe getting closer and closer to something, you need a sense of distance. And so this metric is the right sense of distance to talk about. So this is a concept that we probably won't work with soon, but it'll probably come up later on. So anyways, if you remember in our, this n should be a 3 since this is 3-dimensional, but in 3-dimensional Euclidean space, if you take the inner product of a vector with itself, so a with a, then you end up with ax squared plus ay squared plus az squared. So for example, the first ax comes from the first a and the second ax comes from the second a. But then you'll soon realize that this is very similar to the Pythagorean theorem. And this is just the magnitude of your vector a squared, which is the distance from your vector a to the 0 vector squared. And similarly, you can get the distance between a and b. If you take the inner product of a minus b with itself, then you get, for example, ax minus bx squared plus ay minus by squared plus az minus bz squared. And this is, by the Pythagorean theorem again, the distance between the a and b vectors squared. So then what that means is that if we have an inner product, then we can define a distance by saying the distance between two vectors a and b is the square root of the inner product of a minus b with itself. So this statement doesn't mean much right now since our only inner product that we have is our Euclidean inner product, but in the next video we'll have a different inner product that we'll use later on with Fourier series. And based on that, we can get a distance between functions. So let's see why some of the properties of the inner product were important and how they imply properties for the metric, so that this actually is a proper way to define distance. So remember that we had a property that the inner product of a vector with itself is always non-negative. So the inner product of x with x is greater than or equal to 0. So that means that this inside, since it's the inner product of something with itself, is going to be non-negative, which means that if you take its square root, it's going to be a non-negative real number. So this is one of our axioms for the metric, and that comes from the axiom for the inner product. Secondly, we have that if the distance between two vectors is 0, then the vectors must be the same, because it wouldn't really make sense otherwise to say that if you have the same vector, the distance is non-zero, or if you have the distance between two vectors is 0, then they're different vectors. So we can actually derive this statement by looking at the inner product axioms if we take this metric or length. So the distance between a and b is 0 implies that this inner product is 0. But then based on this, we had another property which was part of our positive definiteness for inner products, which is that the inner product of x with itself is going to be equal to 0. Implies that x is equal to 0. So a minus b is your x here. But if a minus b is equal to 0, then a is equal to b. So that means that these two sides, which is one of our axioms for the metric, is actually satisfied because of the inner product axioms. And then this last one is a bit more interesting, the triangle inequality. So you have the distance between a and b plus the distance between b and c is greater than or equal to the distance between a and c. So b is just some intermediate vector. So it's just saying that the distance between 2 points is shortest if you go direct there, and it's longer if you take any intermediate thing. So here we want to use this definition of the inner product square root and plug those in for dAB, dBC, and dAC and try and prove that this inequality holds. So I'll leave that as an exercise for you to do, but I'll give a hint. So first you have a square root here, so what you want to do is square both sides to sort of get rid of that. And then you'll have an inner product of a minus b, b minus c, and b minus c, and then something else. And on the right side you'll have a minus c and a minus c. And then to simplify your work a little bit, you're going to want to use the linearity property of inner products. So what that means is that you can split up this inner product a plus b with the first argument. So you can take the inner product of a with the second part plus the inner product of b with the second part, which is here. And then you can split up in the second argument. So you can take a with the first part and then b with the first part, or a with the first part here and b with the first part here. And then we have that the inner product of b and a is the inner product of a and b, which is another one of our axioms. So these two are the same thing, and we can combine them into 2 times the inner product of a and b. So then that means that this quantity here is the same thing as the inner product of a with a plus 2 times the inner product of a with b plus the inner product of b with b. And so if you replace a plus b with a minus b, you can derive a very similar relation and use that to prove this triangle inequality. So yeah, that's all I want to say about the metric from the inner product. And so in the next video, we'll talk about the actual inner product that we'll use for Fourier series, and then we'll get pretty close to actually figuring out how to break up functions into sine and cosine series.